My name is Wortmann, and I'm working on a new profiling tool for THC. I talked about it last year, but last year I kind of couldn't really show it off, so this year I want to give a quick demo of what it looks like to use my tool. So, yeah, this works. So first, little introduction so everybody knows what I'm talking about. The big problem with profiling tools in general is that we have a Haskell program at the start. Then THC is going through a great number of steps, and at the end we get a executable code for which we can then get a profile, which we then want to map back to the source code in order to find where the performance problem that we want to investigate was coming from. So how do we do this? We look at what the compiler is doing and do a good bit of bookkeeping on the side to keep track of exactly what came of the source code. So, well, people might say, okay, this is pretty much cost center profiling, isn't it? I mean, this is what all profile things do. Well, I'm doing it a bit differently. What I'm doing is I'm working with THC and I'm trying to not disturb it in any way while it is doing its job, what it is doing best. All I'm doing is I'm keeping the information on the side and updating it so it is as excellent as possible. But if THC really wants to do an optimization, I should say, okay, maybe let's degrade a bit and see what we can still do with the information. This allows me to actually go a lot more low level with my profiling. I can actually do something that C profilers do, which is looking at the instruction pointer and working from there. I'm actually goodly competitive to that. Disadvantages of that: stack traces are already pretty hard with cost centers, this kind of thing, getting the semantics quite right. From the low-level point of view that I'm taking, it gets even harder, which is bad. On the other hand, also at the core stage, a lot of very complicated transformations happen. So that's where I lose most of the accuracy. So it's kind of a disadvantage, it's also kind of an advantage, because it can mean I can focus on explaining the last stage core. And I actually can do that pretty well. I can focus on that. So let's do a demonstration. The example is actually taken from the web. Somebody called Joey Adams posted that on the Stack Exchange code review. And it deals with a pretty simple problem. We have a program which takes a byte string on standard input and wants to escape it to standard out. So just let me quickly just do this. No, I can't. First need to get out of here. Alright. So this is the first version that was written. It just uses, for byte string concat map, uses a function which decides whether or not to escape that character, and then continues on. Well, it tried it, performance wasn't that good. So let's look at a profile of that. Does it work? You see something? Kind of. So yeah. Here's now a view of what this looks like in my profile. We see on the left, that's kind of the first thing we should look at, we see all modules that we have in our program. So we might look at, say, the first one, which happens to be, as I said, I'm very low level, so most cost actually appears to be in the byte string library. So we might look at this and see, okay, here we have the concatenation functions, which seem to be the biggest contenders in this. Here we also see why I talked about losing a bit of accuracy. And concat are obviously the same, kind of, but they are inlined at the same location, so they get the same kind of cost. But just looking at this. So we have used concat map in the program. Here we have concat, which is using a list of byte string. This is pretty much telling us that this is used vanilla. So if we have a large input file, say 10 megabytes, and we're actually constructing here a list with 10 million entries, it can hardly be efficient. Another thing that we might look at is, if we look for our original source file, which appears here, we see that the pack itself is having a lot of cost. And if we look at the core that is always shown here, like the core that got translated from there, we see that this got pretty much translated vanilla. So we see that the list is constructed and everything. That's all very inefficient. So how do we get this more efficient? Well, maybe we shouldn't have used byte string in the first place. I mean, there are special libraries for constructing byte strings. So let's jump to the second version, which uses now place builder, which is a pretty fast library for building byte strings. So, not much to say about this. This is using append and from white and everything, as one should do. Still, performance isn't too good still with this. So, let's look at the profile for this new program. Now we see that the profile has actually changed. We have most cost appearing in this strange SCG pseudo model. If we open that up, we can see that we are actually talking about, these are our runtime system functions. And as I said, a very low level here, so I can actually see the C names here of these. So what does this mean? This means that we actually have, that actually most of the time, the program seems to be spending updating closures, updating things, that's what update framework is doing partial application, that's the second ones. So where is this coming from? Well, we don't have a stack profiling here, but what we can do is we can answer the question, where are all these allocated, by switching to the allocation view. What this now gives us is a view of where the hot allocation points in the core of the program are. So these two are probably not the problem here. These are two basics. Let's look at byte string. Okay, I was saying we were having a lot of closures here that getting applied, but closures, a lot of partial applications. So we're pointed at the go function here, kind of a part of it. So now let's do the actual core diving. Let's look at the core that we are looking at here, right? Core has this, it always seems to rename a lot of things. So what are we looking at here? We can look at the type of this. You actually see this is a builder. It goes from one address to another address. The builder is what we are iterating over. So if we look at this go function, PQ are the addresses at this point. It's probably not directly to see. I'm jumping very quickly here, sorry. You can quickly see that this is pretty much the compiled version of LGO. You can also see a bit down here, actually see here, here's the recursive call. So what are we passing here? What we are passing is actually builder. If we put this up, okay, this is actually a closure, and it actually gets pretty complicated, constructed in a pretty complicated way. What are we actually doing at this point? Well, let's go back to the program report quickly. Here we are. So we work strictly folding over builders. So if you know a bit about the place builder library, is that the builder is entirely actually closure. So we are strictly folding over closures. That's actually what we want. We are creating a huge chain of these closures and not actually doing anything constructive. So this is probably the wrong approach. So if we have a wrong approach, maybe we should try finding a better way of doing this folding. Well, maybe let's just use the one that comes with place builder, say concat, mconcat. It's a monoid after all. Problem always being the monoid takes a list, and for the first example we said we don't want 10 million entries list that we go over. So, but great thing now is list fusion. If you just write it like this, it's actually simplified. Now we actually, before we had this for else something, now we just write mconcat, map, unpack, and actually if we just rely on list fusion, at this point we get, now this got no, we actually get a much better profile, which actually only takes half the time. And if we look at the core code, I mean, okay, I probably don't have the time for that, but we can actually see very good that we have at least eliminated a few closures there and have much better core code. So let's quickly go back to the slides. Oops. Here we go. So what we learned from that, by the way, is that sometimes it's actually not it's not the best way to introduce more strictness, but sometimes it can just be the answer to rely more on the magic behind the scenes with Haskell. So, if you want to try this, if you think this could help you in your task, then this is a short version. You need to have Linux. Sorry, I haven't gotten around to really port it so far. You need LLVM as the backend and a library, and then you need to build your own GHC and thread store for the whole thing. Sorry, I guess that's the hardest part. A detailed how to can be found here. And thank you for listening, and I have to thank
One quick question, and we'll save the rest for the break. One? Awesome.
Yeah. Thank you.
Yeah. All right, we'll save them for a break. Thank you very much.